all know what this is. Many of us know how to play it. But the real question is, do you know how it actually works? Like, why if I play A major, it sounds like A major, and G major, it sounds like G major. In order to understand that, we need some basics of acoustics and harmonics, which will be understanding in the further video.
A sound wave is produced by a vibrating object. As a guitar string vibrates, the vibration translates through the neck and the bridge to the body of the guitar, which sets the surrounding air molecules into vibrational motion. The back and forth vibration of the string produces a sound wave with rarefactions and compressions, which propagate to our ear, which translates them into electrical pulses, and the brain eventually interprets it as sound. The frequency at which these air molecules vibrate is equal to the frequency of vibration of the guitar string. Now, listening to the same frequency over and over again would be boring, right? What makes a guitar interesting is that a guitar string has a number of frequencies at which it will naturally vibrate. Each of these frequencies is associated with a standing wave pattern, and the vibrations satisfy the relationship V is equals to N lambda.
Standing waves. It is a combination of two waves moving in opposite directions, each with the same amplitude and frequency. This phenomenon occurs as a result of interference. There are 2 points to be noted on this wave: the node, which is where the wave has minimum amplitude, and the antinode, where it has maximum amplitude. The string of a guitar is an example of a string fixed at both ends. The vibration of such strings sets up standing waves, but it can only vibrate in a few very specific ways as defined by the boundary conditions. The two fixed ends are the node points, and therefore the only possible ways are as shown. All of these possible modes of vibration are called the harmonics. The fundamental frequency, which is the lowest tone, is one where the wavelength of the wave on the string is twice the length of the string itself. That is, L is equal to lambda by 2. The first overtone, or the second harmonic, satisfies the condition L is equal to lambda. Each higher overtone fits an additional half wavelength of the string. Thus, wavelength of the nth harmonic is given by lambda n is equal to 2L by n. The string does not vibrate in one of these harmonics, but many at the same time, which produces a complex waveform of multiple frequencies. But the fact to be noted is that harmonic frequencies are integral multiples of the fundamental frequency. This is part of the reason why such instruments sound present.
However, the question that arises is, how is it possible for us to have a different frequency for each string? For this, we need to see the various factors on which string frequencies depend. Since the fundamental wavelength is twice the distance between the bridge and fret, all 6 strings use the same range of wavelength. To have different frequencies, then, one must have different wave speeds. The speed can be varied by either changing the tension or the mass density. So in terms of these two physical quantities, the fundamental frequency of an ideal string fixed at both ends is given by this equation over here. If we wanted to express the fundamental frequency of a string in terms of its radius, we can use the volume mass density ρ, and the equation changes to this. This shows us that for strings of the same length, the same density, and experiencing the same tension, the thicker string will have the lower fundamental frequency and consequently a lower pitch.
Now that we know about basics of harmonics and how these chords work, next time you hear any string instrument, just remember the string theory behind it.